Good morning, students. Chapter 6, Electromagnetic Induction. Okay, yes. In this chapter, we have to discuss about, due to change in magnetic flux, EMF is induced, current is produced. Okay, now next concept is inductance. What is inductance? We will discuss in this lecture. See, if I have one coil, if I have one coil which is connected with AC source, for example. Okay, so yes, current is flowing from this coil. If we have another coil which is connected with galvanometer, so yes, as it is AC current, value of current in this case changes due to that magnetic field produced due to this coil changes. This magnetic field is linked with this coil, yes or no? Magnetic field is linked with this coil. So yes, due to that magnetic field, flux is linked with this coil. Now if current changes, magnetic field changes, flux changes, and we know that EMF is induced. Clear about this? Okay, so yes, if there is current flowing in one coil, EMF is induced in another coil, current is induced in another coil. Clear about this? Okay, EMF is induced in coil because there is some flux. Okay, now if second case, if I have one solenoid, it is rheostat connected with battery. Okay, rheostat means variable resistance. So yes, if resistance is variable, current flowing from this solenoid is also variable. So yes, current flowing from this solenoid is also variable. So in this case, what happens? Yes, current is flowing from solenoid. So inside solenoid, magnetic field is produced, and this magnetic field is linked with solenoid itself. Yes, current is flowing in this coil, magnetic field is produced in this coil, and flux is linked. Flux is linked with coil itself. Here, current is flowing in first coil. And flux is in second coil. Flux link is in second coil because EMF here is induced. EMF is induced in second coil. EMF is induced in second coil. While in this case, what happens? Current is flowing in this coil. Magnetic field is produced in this coil. Flux is also linked with this coil itself. And if there is change in current, there is change in magnetic field, there is change in flux, then EMF is induced. In same coil. So yes, in these two cases, concept is same. Due to current, magnetic field is produced, flux is linked, and due to change in flux, EMF is induced. But here, current is flowing in one coil, and due to that, EMF is generated in another coil. While in this case, current is flowing in this coil and EMF is also induced in the same coil. Yes or no? It is called mutual inductance. Okay, and it is called self-inductance. Clear about this? So yes, mutual inductance, two coils. Self-inductance, only one coil. And see, if you understand, in these two cases, this total flux linked with coil, this flux linked with coil, it depends on I. It depends on I, because current is flowing, due to that magnetic field is produced, and due to that flux is linked with coil itself, in this case, or with another coil. Clear here? Okay, so now how to write? Okay, here flux linked with coil is directly proportional to current. Directly proportional to current. Okay, here flux linked with coil is directly proportional to current. If flux linked with one turn is phi, and we have total n turns in both cases, if we have total n turns, okay, then total flux n phi is directly proportional to current. Clear about this? And yes, this n phi, it is called flux linkage. Clear about this? So yes, flux linked with coil is directly proportional to current, that is total flux n phi is proportional to I, where n number of turns in coil and phi flux linked with each turn. Clear about this? Okay, so yes, this n phi is proportional to I. If we remove proportionality, we have to add some constant. Yes, if we remove proportionality, we have to add some constant, and that constant is called inductance. Clear about this? How to write? See, okay, therefore n phi is equal to Li. Therefore, L is equal to, here it is n phi upon I, where this L is called inductance. This constant of proportionality is called inductance. Clear about this? What is inductance? Total flux per unit current. N phi upon I. Total flux. N phi is total flux. And I is current. Clear about this? So yes, this thing you have to remember. Okay, what is total flux? Okay, I, it is called inductance. So yes, it is inductance. L is equal to n phi upon I, total flux per current. What is its unit? Its unit is Henry. And it is denoted by capital H. Clear about this? Now, this inductance depends on number of turns in coil, then shape and size of coil, and then medium inside solenoid or coil. Clear? So yes, this inductance depends on shape and size or geometry of coil, and medium inside the solenoid, inside coil. Okay, for example, inside the solenoid there is air. If we replace air, then yes, its inductance changes. Clear about this? Okay, so yes, it is all about inductance. What is inductance? Okay, flux linked with coil is directly proportional to current, that is total flux n phi is equal to proportional to I. N phi is for flux linkage and number of turns in coil, phi flux linked with each turn. N phi is equal to Li, where Li is called inductance. Its unit is Henry. Clear about this? Okay, inductance depends on numbers of turns. of coil, shape and size of coil, medium inside solenoid, medium inside solenoid. Clear about this? Any doubt? And yes, for given coil, inductance is constant. For given coil, inductance is constant. Clear about this? Clear about this? Yes, this inductance, we can compare this inductance with capacitor. Capacitor, two conductors, yes or no, two conductors insulated from each other, means there is insulating property, dielectric object between two conducting plates. So capacitance depends on separation between them and also medium between them. So yes, we can compare this inductance with capacitor. Clear about this? So yes, it is one topic, that is what is inductance. What is inductance? Now we will see in detail what is mutual inductance and what is self-inductance. But again, to find inductance, we have to find total flux per current. Total flux per current. Clear about this? For mutual inductance, we have to flow current in one coil, flux in second coil. But for self-inductance, in the same coil, current, and in the same coil, flux. Okay, so it is difference. We will see in detail. See, here it is. Now we will see mutual inductance in detail. Okay, yes, for mutual inductance you have to consider two coils. Let two coils are like this. It is first coil, coil 1. Okay, we have two coils. Let it is coil 1 and another coil is like this. Another coil is like this. Okay, so yes, we can say we have two coils coaxially because their axis is common. Yes, radius of small coil is R1 and radius of another coil is R2. Clear about this? So yes, we have two coils. Okay, two coils having same axis. Okay, now we have to assume some data for coil 1 and for coil 2. Okay, let radius of coil 1 is R1, radius of coil 2 is R. Clear about this? Numbers of turns, total numbers of turns. Okay, total numbers of turns. And 1, here it is, and 2. Clear about this? Total numbers of turns, and 1, and here it is, and 2. Okay, then length of 2, here taking same length, L and L. Okay, here taking the length same. Clear about this? Okay, so yes, we have two coils having same axis, coil 1 and coil 2. Radius R1, R2. Numbers of turns N1 and 2. Length is L and L. Yes, numbers of turns per unit length. Number of turns per unit length. Number of turns per unit length means N1 is equal to N1 upon L. Yes or no? And here N2 is equal to, here it is N2 upon L. Clear about this? So first of all, it is data. First of all, it is data. Clear about this? Then what is R1, R2, N1, N2, L, N1 and N2. Clear about this? Now we have to find what is mutual inductance. So first of all, we will flow current in any one coil. We will flow current in any one coil. Okay? Yes. Let I1 current is flowing from coil 1. So yes. Let I1 current is passed from in coil. Let I1 current is passed in coil 1. In coil 1. So yes, I1 current, okay, take care about this. I1 current is passed in coil 1. So in coil 1, magnetic field is produced. That magnetic field is linked with coil 2. So in coil 2, there is some flux. Yes or no? Yes or no? Yes. Okay. Okay. Let I1 current is passed in coil 1. So total flux linkage linked with coil 2, that is N2 phi 2 is proportional to I1. Clear about this? Total flux linked with coil 2, N2 phi 2 is proportional to I1. So yes, here I can write it is N2 phi 2 is equal to, it is M21 I1, where M21 is called mutual inductance, of coil 2 with respect to coil 1. Clear about this? So yes, it is nothing but inductance that we have discussed in previous section. Clear about this? Now we have to find what is equation of M21. We have to find what is equation of M21. That is equation number 1. Okay, see here it is. See here it is. How to find this N2 phi 2? That is flux linked with coil 2 N2 phi 2. How to find? Take care. Here it is. N2. From this way, N2 is subject. N2 means total number of turns in coil 2. So total number of turns in coil 2, I can write this N2. Clear about this? Now phi 2. See, in coil 1, current is passed. So due to that current, magnetic field is produced, and that magnetic field is linked with coil 2. That magnetic field is linked with coil 2. Clear about this? So now here we have to use equation of flux. That is it is A2 B1 cos theta. It is A2 B1 cos theta. Flux, equation of flux. A2 B1 cos theta. Why A2? Because we have to find flux linked with coil 2. Why B1? Because magnetic field is produced due to coil 1, because current is flowing in coil 1. Clear about this? Okay, just you have to understand only this equation, then it is easy. Flux linked with coil 2, that is N2 phi 2. Total number of turns in coil 2 is N2L. Phi 2, flux linked with coil 2. Its equation is A B cos theta. Why A2? Flux linked with coil 2 you have to find. And B1, because current is passed from coil 1 and magnetic field is produced due to coil 1. You have to find flux linked with coil 2. Clear? So now, what is A2, what is B1, and what is cos theta, that we have to find. So yes, is equal to N2 phi 2 is equal to N2 phi 2 is equal to, here is N2L. A2 means area of this cross-sectional area of this coil 2, whole, not whole. See why? What is reason? Here current is passed in coil 1. So magnetic field, yes, magnetic field is only inside this coil. Yes or no? Is only inside this coil. Magnetic field is only inside this coil. Okay, so magnetic field we can say it is only in this region. Magnetic field we can say is only in this region. If I draw its cross section like this, okay, magnetic field is only in this region. In this region there is no magnetic field. In this region there is no magnetic field. So yes, as we have to find flux linked with coil 2. Okay, yes. At first sight we can say A2 is equal to pi R2 square, but no, here as in this region magnetic field is 0, here flux is equal to 0. So flux is passing only from this region. Flux is passing only from this region. So here, yes, this radius is it is R1. So here as A2 I have to write, here it is as A2 I have to write pi R1 square. Pi R1 square. Why pi R1 square? Okay, understand again. Current is passed in coil 1. Yes or no? Yes. Magnetic field, we know that in solenoid, in coil, magnetic field is only inside, outside magnetic field is 0. So magnetic field is only in this region, So flux is also linked only in this region. In this region and this region there is no flux. So yes, we have to consider only this cross-sectional area. Clear about this? Okay. Now how to find? See, yes, B1 is magnetic field due to coil 1. In coil 1, current is passed I1. In coil 1, number of turns per unit length is N1. Then what is equation of magnetic field? Yes, equation of magnetic field B1 is equal to, it is mu 0 N1 I1. Cos theta, yes, magnetic field is actually, yes or no? Yes, it is actually, okay, and if this cross-sectional area is also in this direction. So yes, cos theta, here angle will be 0, so here it is cos 0. Clear about this? So yes, in this whole thing, you have to take care about this step only. Okay, if you understand this step, then theory is easy. Okay, so now therefore N2 phi 2 is equal to here is N2 L pi R1 square mu 0 N1 I1. Any doubt? Now take this I1 this side, so N2 phi 2 upon I1 is equal to, first of all I will write mu 0. Okay, I will write mu 0. Okay, first of all I will write here it is mu 0, then N1 and then N1 and then pi R1 square, here it is L. Pi R1 square, here it is L. Now this N2 phi 2 upon I1, from this N2 phi 2 upon I1 make it subject, it is nothing but M21 is equal to, here it is mu 0 N1 N2 pi R1 square L. It is equation number 1. That is mutual inductance of coil 2 with respect to coil 1. Mutual inductance of coil 2 with respect to coil 1. Clear about this? Now with similar method, we will find M12. With similar method, we will find M12. How to find M12? See, here it is. Here. Similarly, yes, I have to write. How? Let I2 current is passed in coil 2. So total flux linked with coil 1 N1 phi1 is proportional to I2. So yes, if I remove proportionality constant, N1 phi1 is equal to M12 I2, where M12 is called mutual inductance, of coil 1 with respect to coil 2. Clear about this? Now again, I have to find flux linked with coil 1. That is N1 phi 1. Yes, how to write N1 phi 1? N1, from this if you make N1, it is N1L. It is N1L. Clear about this? Now phi 1 means current is passed from second coil. Magnetic field is produced in second coil. That magnetic field is linked with first coil. So flux is linked in first coil. So how to write this equation? This equation A1 B2 cos theta. A1 B2 cos theta. Clear about this? So yes, is equal to, here it is N1L. A1. Yes, you have to find flux linked with this small coil. And its area is pi r1 square. Its area is pi r1 square. Clear about this? Yes, in second case what happens? It is small coil. Okay, and it is large coil. Okay, now magnetic field is produced in this large coil. Yes or no? Like this. But you have to find flux passing from this small coil. And its area, it is only this, that is pi r1 square. Clear about this? Then how to write this equation? N1 phi is equal to N1 and A1 it is pi r1 square. B2, how to find B2? Like this. B2 is equal to, it is mu 0 N2 I2. And cos theta, again theta will be 0. So here it is cos 0 means this one. Clear about this? So now take this I2 this side. So N1 phi 1 upon I2 is equal to, if you arrange these terms again, then mu 0 N1 N2 pi R1 square, and here it is L. So therefore it is called M12 is equal to mu 0 N1 N2 pi R1 square. It is coefficient, it is mutual inductance of coil 1 with respect to coil 2. Now observe these two equations. See, M21 and M12, mu 0 N1 N2 pi R1 square L, mu 0 N1 N2 pi R1 square L. So yes, from this we can say, if we have two coils, coil 1 and coil 2, and if you find mutual inductance of coil 1 with respect to 2 or of coil 2 with respect to coil 1, that is M12 and M21, they are same. So yes, here I can write M12 is equal to M21 and is equal to, I can write M, and is equal to, I can write mu 0 N1 N2 pi R1 square L. It is pi R1 square L. Clear about this? So yes, it is one theorem. Yes, your question is like this. If for two coils, prove that M12 is equal to M21 is equal to M. You have to prove this equation. Okay, mutual inductance of coil 1 with respect to 2 and of coil 2 with respect to 1. It is same. Clear about this? So yes, it is one equation that you have to prove. Now, how to find mutual EMF? See, we will see this topic. Mutual EMF. Okay, now see, again, let I1 current is passed in coil 1, total flux linked with coil 2, and 2 phi 2 is proportional to I1 and 2 phi 2 is equal to M21 I1. Now I can write N2 phi 2 is equal to Mi1. Why M? Because we have proved M21 is equal to M12 is equal to M. Now if I differentiate this equation with respect to time, differentiate this equation with respect to time, let's see how to write d upon dt. N2 phi 2 is equal to d upon dt Mi1. Clear about this? Now d upon dt of N2 phi 2 is equal to d upon dt of Mi1. Now, yes, we know that according to Faraday's law, E2 is equal to minus d upon dt of N2 phi 2. Yes or no? It is nothing but Faraday's law. EMF is equal to it is time rate of change of flux, d upon dt of N2 phi 2. So yes, here d upon dt N2 phi 2 I can write as here this E2. Okay, this minus sign I will write right hand side. So here it is minus M, mutual inductance constant. So here it is di1 upon dt. E2 is equal to it is minus M di1 upon dt. E2 is equal to it is minus M di1 upon dt. Clear about this? Similarly, if current I2 is passed in coil 2, then what is flux linkage? With coil 1? Flux link in coil 1, that is N1 phi 1 is equal to, yes, we know that it is M1 to I2. Yes or no? Yes, it is. Again, if we differentiate this equation with respect to time, then we will get d upon dt of N1 phi 1 is equal to d upon dt. Yes, I can replace this M12 by only M. Okay, it is M I2. So again, according to Faraday's law, we can say here it is E1, it is minus sign M di2 upon dt. di2 upon dt. Clear about this? Yes, minus sign indicates Lenz's law. Minus sign indicates Lenz's law. Okay, that EMF is induced which opposes its cause. So here in mutual inductance, see what happens. Current is passed in coil 1 and EMF is induced in coil 2. Current is passed in coil 2 and EMF is induced in coil 1. So it is called mutual inductance. Clear about this? You have to remember these equations. Clear about this? Any doubt? So yes, in this lecture we have discussed about what is inductance and what is mutual inductance. First of all, for mutual inductance you have to obtain one relation between M12 and M21, they are equal. And then what is mutual EMF? This E1 and E2, they are called mutual EMF. Clear? So now in next lecture we will discuss about self-inductance. Okay, when current is passed in a coil, flux is linked with coil itself, and EMF is induced in coil itself. Okay, about self-inductance we will see in next lecture. Dear students, chapter 6, electromagnetic induction. Yes, it is second last theory of this chapter. Watch regular videos. If you have any doubt, then contact me. I will try my best to solve your doubts. Okay, yes, you have to make regular notes, appear for exam regularly, and yes, regularly you have to comment, like and share our videos, and especially mine. Okay.